Welcome to lecture 12. In the previous one, we just looked at the stresses at a point and the components of stress on any arbitrary plane, and then we looked at the principal stresses, maximum shear stress. So what the concept we discussed were, now please remember, stress at a point is described by sigma x, sigma z, tau xz is equal to tau zx. So if I have more than two components, remember the scalar has only one component to describe. A vector has two. That is, here I have magnitude only. When I say I'm going, my speed is some, it means that I'm going at a certain distance per minute or per hour. Vector gives me the magnitude and direction. Now this stress is called tensor because you need at least three components in case of a plane problem, and you would probably need 6 components in a general three-dimensional one. Then we talk of sigma x, tau xy, tau xz, tau yx, sigma y, and tau yz. Then tau zx, tau yz, and sigma z. So a stress at a point in 2 dimensions has 3 components, and general 3 dimensions it has 6 components, and that's why we call it as a tensor. From there we calculated the principal stresses sigma 1 and sigma 3, and then we had maximum shear stress. In the Morse circle, if you have seen, if the direction of sigma 1 and sigma 3, what is the angle? This is 180 degrees. So in real life you will have two directions will be pi by 2. This will be the major and minor principal stresses. Let us say sigma 1 and sigma 3. Now the angle between major principal stress and tau max, or sigma 3 and tau max, is 90 degrees, which means 45 degrees. So if I now draw another element at an angle 45, you will find that the shear stresses are maximum. So please remember, there is always this 45-degree rotation between the major principal stresses and the maximum planes of maximum shear stress. Another concept I introduced was the stress point. Let us say I have a small element on which I have sigma 1 and sigma 3. These are the major principal stresses. I will say the tau is 0, shear stress are 0. So can I say in the Morse circle, I get a simple circle, and of course both sides. So this will be sigma 1 and sigma 3. The center is given here and the radius here. So this is the point A. The stress point is called A, let's say. What are the coordinates of A in the stress space? The x component, or shall we say sigma component. I define it as P is sigma 1 plus sigma 3 by 2, the average of the two principal stresses. The y component, the tau component, is Q, which is equal to sigma 1 minus sigma 3 by 2. This is distance to the center, and this is the radius of the Morse circle. So if I are given the two components, you know immediately how to locate the Morse circle. The center and the radius is given. I want you to now visualize, as a civil engineer, what will you do? I have the ground here, and already there is some state of stress, sigma 1 0, sigma 3 0. Let us say we build a structure, which means we can increase this load in the vertical direction. So if I increase the load by vertical direction, what will happen to, say, Pi is equal to sigma 1 plus sigma 3 by 2, and Qi initially is sigma 1 minus sigma 3 by 2. But after you apply the load, that is, you have constructed a structure, could be multi-storied structure, it could be a water tank, it could be an embankment, a bridge, whatever it is. All of them have certain weight. So the weight will cause an increase in the vertical stress sigma 1. So then I say the final vertical stress would be sigma 1 plus delta sigma. So what will be the final P? It will be equal to sigma F plus sigma 3 by 2. Q final is sigma F minus sigma 3 by 2. Now you can see that PF is equal to sigma 1 plus sigma 3 by 2 plus delta sigma by 2, whereas here again sigma 1 plus minus sigma 3 by 2 plus delta sigma by 2. What happened? You will find that PF and QF have increased. So basically what you have got is a different mode circle and the point goes up because this is sigma final. Now instead of drawing so many circles, what we say is that why not simply show point A to A prime. What are the coordinates of A prime? PF and QF. How did you get PF? Sigma F plus sigma 3 by 2, which is same as sigma 1 plus sigma 3 by 2 plus half of the increase in the vertical stress. Similarly, QF is equal to sigma F minus sigma 3 by 2, sigma F minus sigma 3 by 2, which is sigma 1 minus sigma 3 by 2 plus sigma delta sigma by 2. So it becomes very easy to show the change in stress, in which direction is it going. Can I say that this will be in the first quadrant of the coordinate system? Sigma is increasing, so both P and Q are increasing. So we also plot, instead of sigma 1 and tau, can I plot in terms of P and Q? These are very simple definitions, so you should not have any problem. Suppose I plot P and Q, and it's easy for me to now say this is point A, this is point A prime. So the stresses in the soil go from A to A prime, and this is called the stress path, which has a very, very important application because the behavior of the soil is a function of the stress path. When you constructed the building, we have increased the load on the ground. Suppose instead of that, I have excavated. The ground was here, original ground level. I have removed 5 meters of the soil. So what happened to the stress here? We have removed the load. So what is the direction now? Magnitude and direction. Delta sigma becomes, instead of positive, becomes negative. Please remember, when you are excavating, you are removing material. In that case, you will find that the P and Q will decrease because sigma 1 is decreasing, and the stress path would be A double prime. Suppose you allow sigma 3 to decrease. Keeping sigma 1 constant, you will find the stress path will go in the second quadrant. If you increase sigma 3, it will go into the fourth quadrant. What we say is in a slightly different way. The 4 quadrants will be, the initial point is here, increase in delta sigma 1, delta sigma 3 is 0. There is no increase in that. Whereas here, delta sigma 1 is decreasing, delta sigma 3 is of course constant. And in the second quadrant, delta sigma 1 is constant, delta sigma 3 is decreasing. And the last one, where horizontal stress is increasing. So you will get 4 different stress paths. Stress path 1 for loading, 2 unloading due to decrease in horizontal stress, 3 is unloading due to decrease in vertical stress. Lastly, stress path 4 is due to loading, increase of horizontal stress. When I say this is increase in vertical stress. So 4 activities we do. You may ask me, where am I getting this? Suppose you have a retaining wall and you have constructed here and the soil here. How does it experience if the wall moves here? Wall is moving away from the soil, then you will have the lateral stress decreasing. Instead of that, suppose I'm pushing the wall here. In a excavation, I put in a strut and then I push the soil back, in which case I'm increasing the horizontal stress, and I find that sigma 3 is increasing, and that is why I get stress path in the fourth quadrant. So this is how we try to visualize changes in the ground due to civil engineering activities. Now let's look at what kind of stresses exist in the ground. Let us say this is the ground level. We have a soil with unit weight gamma. There is no water. It's a dry soil. So gamma is equal to gamma dry or gamma total, whatever you want to call it. Let's say equal to something like 17 kilonewtons per meter cube. If I take a small point at a depth z, let's say z is equal to 5 meters. You take a small area. What will be the stress if I take a unit area? What will be the force? Is due to the weight of the soil up to this point. That is equal to, area is equal to, say I'm taking 1 and volume will be 1 into z. So the weight is equal to gamma total into volume, which is equal to gamma t gamma total into z. And what will be the stress? I'll call it z, sigma z, vertical stress. It will be equal to gamma t into z by area, which is equal to 1. So you find that this stress, vertical stress, and we'll say due to gravity. Gravity is acting downward always, the acceleration due to gravity of the earth. Every element on the surface or even in the sky up to a certain distance into the stratosphere, they're all affected by the gravity. So the gravity stresses, vertical stress, we call it sigma z, is equal to gamma into z, which means the stresses keep increasing with depth. If I want to plot now, and I have z, it increases. And what is the rate of increase? Gamma t into linear function. Suppose you have two different soils. What happens? Ground level, 3 meters, I have, let's say, a dense sand, gamma T1, let's say is equal to 19 kilonewtons per meter cube. And below that is something like medium dense silty clay, which is unit weight gamma T2 is only 16.5 kilonewtons per meter. They are different soils. So as far as the stresses in the top layer are concerned, they will increase at the rate of 19 kilonewtons per meter cube. So as you can see here, in this case, but once you reach the interface, what is the unit weight? Unit weight is not 19, but it will be 16.5. So the slope changes slightly, and the unit weight here is gamma T2 into whatever is the depth. Now I have to calculate these two. So what will be the stress here? It starts with 0. At a depth of 3 meters, this becomes 57 kilopascals, kilonewtons per meter square. From here, I have to calculate based on gamma T2. So I'll have to calculate stress here is equal to gamma T1 into H1, if I call this, plus gamma T2 into Z minus H1. What is the depth within the second layer? I only have to use that. So for depth greater than 3 meters, I'll have to subtract the first layer thickness and find out the net thickness in the second layer, multiply this with unit weight of the second layer. Let's say I'm interested at Z is equal to 5. Then what will be this stress? Sigma Z at 5 meters will be equal to 19 into 3 plus 16.5 into 5 minus 3. This is 57 plus 16 to 33. So it will be 90 kb. So you know how to calculate stresses up to the first layer and stresses in the second layer by simply adding these two. But when you are calculating for the stress increment in the second layer, you have to take the reference depth as the bottom of the first layer. Now suppose in the ground there is groundwater level. As I said earlier in one of my lectures, that everywhere or in most places, if you have the ground level, we will have groundwater level. What is groundwater level? It is the level up to which the water will rise within the ground, and if you had a well there or a tube well, you will find the well at the top of the water level. It's very easy to find out. So when we do the soil investigations, we make a hole 150 mm diameter, put a casing and wait for a day. If there is water table, it will rise up to the top of it, and that is the phreatic surface below the ground level, which we call as groundwater level. If you are in a coastal area or near a river bed, you may, for all I know, you will have the water level. It's not groundwater level, but it can be above the ground too. This is what you call as the standing water. Or can I say ground is submerged. Let's find out how to calculate the stresses when you have groundwater level. Now let's again look at here. What will be the unit weight of the soil below the water table and above the water table? Can you say that all the soil below the water table is fully saturated? Because water is there all the time, all the voids get filled up with water, so you have gamma saturated. And above the water table, it may be saturated or it may not be saturated. So I'll use the word gamma T. So here is ground level, and let us say this is the depth to water table is HW. HW, I was telling you, can be variable. Now we are in September, maybe end of September, early October, this groundwater table will be very high. As we draw water for irrigation, drinking, whatever it is, or due to evaporation, you find the groundwater level falls down, and maybe in May it will come down to some deep depth. So depending on the location of the groundwater level, we'll have to calculate the stresses. So in the present case, let us say this groundwater level is at a depth of 4 meters from ground level in one of your sites. Then how do I calculate the total stresses? The stresses due to weight of soil. For Z less than or equal to 4 meters, shall I say sigma Z is equal to gamma total into Z. What is the unit weight? Above the water table, gamma T. So I'll say the vertical stress is gamma T into Z. Let us say the unit weight is only 17.5 kilonewtons per meter cube. So the vertical stress will increase from 0 to a depth of 4 meters. Sigma Z is equal to 0 at ground level. Sigma Z is equal to 17.5 into 4. That will work out 35 into 2, 70. Or you can write kilopascals. Once you take the depth below the water table, what is the unit weight I should take? Should be gamma saturated. Just as we looked at 2 unit weights, we'll have to look at the unit weight below the water table. For Z greater than 4 meters, greater than or equal to, sigma Z is equal to gamma T into 4, shall I say as a general word HW, the depth to groundwater level, plus gamma saturated Z minus HW. So how do I calculate? Again, if I substitute Z is equal to 4, this will cancel, so I'll get the back. Suppose I want Z is equal to 6 meters. Then sigma Z at 6 meters is equal to 17.5. Gamma saturated I didn't give you, it's 19 kilonewtons per meter cube. This is equal to 17.5 into 4 plus 19. What is the depth? We said 6 meters. What is HW in this case? 4 meters. So this becomes 70 plus 38. This becomes 108. In this case, unit weight is higher below the water table. So our plot shows a steepening of the gradient or the line. So it's very easy to calculate at different points above the water table and below the water table. That's how we can calculate. Now I'll introduce something very interesting with the water table. Suppose now let me put a small standpipe or a piezometer at a depth equal to, let's say we said 6 meters. I have put in a simple pipe corresponding to the point here. If I put the pipe here, is there any water above the water table? There's no water, so there will be no standing water. But now if I put a pipe here corresponding to depth, would you agree that the water level will rise up to the groundwater level? Which is a simple concept that if I have a bucket of water, we said the water pressure is a function of the depth of the point you are measuring from the top of the level. You agree that soils have interconnected voids, so the water is continuously connected to the groundwater. The water pressure here is atmospheric. We are now only talking with respect to the atmospheric pressure, so you find that the water table will rise, or the water level in the tube will rise up to groundwater level. So can I say the pore pressure will be equal to, so what you have found out is the total stress here at 6 meters, sigma z is equal to 70 plus 3808. That is the total downward force. But in the pore water, the pressure is corresponding to the depth from the top of the groundwater level to the point. So this distance is 2 meters. So corresponding to 2 meters, unit weight of water is 9.81 kilonewton per meter cube. So the pressure will be equal to 19.6. So can we now plot on this how the pressures vary? I'm plotting now not only the total stress, but I can also plot the pore pressure. Pore water pressure. To make it short, we say pore pressure. Basically what it means, the pressure in the pore water. This is equal to U is gamma W into Z minus the depth to the groundwater level. Please remember, the groundwater level is at a depth of 4 meters, HW. So the water pressure will only increase from the top of the groundwater level and below. So you find that now the pore pressure is equal to gamma W into Z minus HW. This is equal to 19.6. 19 point, yeah, kPa. So out of the total of 108 kilopascals, 19.6 or 20 kPa is taken by the water. Where is the other stress going? We have a total vertical stress of 108 kilopascal at a depth of 6 meters. And you find that the water is taking only 19.6. Then the difference between these two is called the effective stress. Is we represent with a prime. What is effective stress? It is the stress carried by soil solids, or we can say grains. This is one of the most important concepts. Effective stress is the stress carried by soil grains. Soil grains don't carry all the vertical stress. The water within the pores will carry part of it. This can be calculated easily. Suppose you have submerged ground. How do you calculate? Here is the water level and this is the ground level. You are doing an offshore project and this is the sea level. Let's say this depth to water is dW, and then the soil here obviously will be gamma saturated. Here it is gamma water. So now if I plot here, can I say pore pressure U will increase? U is a function of gamma W into Z. Pore pressure will increase uniformly with respect to depth, and the gradient or the rate of increase is equal to gamma W into Z. What about the total stresses? Here it is increasing at gamma W into Z. But then once you come here, I'm now plotting sigma Z. Sigma Z will be equal to, for Z greater than dW, depth of water level, gamma W into dW plus Z minus dW into gamma saturated. What is the unit weight of the material below the ground level? It's gamma saturated. So what you have done is, above the ground level, it is only water. So I'm just taking for Z less than dW, vertical stress, which is equal to pore pressure, is nothing but gamma W into Z. But below the ground level, the rate of increase is now dependent on gamma saturated. So what you find now would be that this difference will give us the effective stress. This is sigma Z, this is U. So the effective stresses keep increasing with depth because there is more soil, and the pore pressures also increase, but the unit weight is increasing, and unit weight is higher for the saturated soil than that of water. So you find that for the pore pressure, it's equal to gamma W into Z, whereas the total stress increases much faster from the ground level onwards, which will be equal to the water stress due to water above the ground plus the stress due to saturated soil. And this is how the total and pore pressures vary. The difference between these two is what we call as effective stress, is the difference between total stress and the pore pressure. So let us write the definition. Minus is equal to the effective stress. Another way we write the same thing would be total stress is equal to effective stress plus pore pressure. So we say sigma is equal to sigma prime plus U, or sigma prime is equal to sigma minus U. This is one of the fundamental laws of geotechnical engineering, wherein we say the applied stress, the gravity stresses, whatever they are shared by the interparticle grains, that is the effective stress, and the pore water pressure. The basic theme, which was given by Tazagi, is that all soil behavior is controlled by effective stresses and not by pore pressure. So please remember, effective stress principle has two components. One is sigma, the total stress is equal to effective stress plus pore pressure. The second part, which he says all soil behavior is, let me write in a big way, you will never forget it. Please remember this, whether it is strength, deformation, whatever it is. You may increase the total stress. If the pore pressure is increased, the effective stress will not change. If effective stress does not change, the soil does not change in its behavior. It will not increase in its strength, it will not show any deformation, and so our analysis will be not correct because we are not able to identify what is happening. So what Tazagi gave in 1925 and later is the effective stress principle, which is the basic thing for all soils, and we now like to look at that as the starting point for all our analysis. There is one more parameter that we need to talk, that is, if I know the vertical stress, this is the vertical stress. Shall I now say it is the total vertical stress, and U is the pore pressure. So sigma Z prime is the effective vertical stress. You know how to calculate sigma Z, you know how to calculate U. Then basic law again, the second one would be, if I say sigma H prime is the effective horizontal stress in the ground. I'm looking at now a small element. This we said is sigma Z. Then you can have sigma H, and you will have pore pressure. So I'll say sigma H prime sigma z prime. I'm looking at a small element at a depth z below the water table. This is the groundwater level, this is the ground level. At this depth, vertical stress is sigma z, pore pressure is u. So you have calculated sigma z prime. What the law again says, or we find that sigma is equal to, where k naught is called coefficient of earth pressure at rest. There is a relation between the vertical and horizontal stress, effective stresses only. Please remember, effective horizontal stress is k naught times sigma z, or k naught is equal to sigma h prime by sigma z prime. Please remember, it's only the ratio of effective stresses and not the total stresses. So what will be the total horizontal stress? Sigma h is equal to sigma h prime plus u. Why? Because you know pore pressure or water pressure is hydrostatic. It doesn't depend on direction. I can have the same pressure in any direction at any point. So I find it out, and that will be equal to k naught times sigma z prime plus u naught, whatever is the pressure. So now we have sigma z prime, u sigma h prime, and sigma h. What are they? Total vertical stress, effective vertical stress, pore pressure, effective horizontal stress, and total vertical stress. So this gives us the complete picture of state of stress within the ground in the natural condition. We'll pass on to the effective stress principle and its application later. Okay.